Hello friends, welcome back to my channel. Today I'll be discussing a numerical based on molecular diffusion in multi-component gas mixture. In my previous video which I posted on my YouTube channel, I have discussed molecular diffusion in multi-component gas mixture, and based on that discussion I'll be discussing one numerical in today's video. I'm giving link to that video in the description section. So those who have not yet seen that video, you please watch the video and then follow this numerical. So this is molecular diffusion in multi-component gas mixture, and we are going to discuss one numerical based on that. Okay, so let us go and discuss the numerical. So first I'll show you what is the statement of the numerical that we are supposed to solve. The statement goes like this: ammonia is diffusing through a stagnant gas mixture consisting of 1/3 nitrogen and 2/3 hydrogen by volume. The total pressure is 206.8 kilonewton per meter square and the temperature is 54 degrees Celsius. Calculate the rate of diffusion of ammonia through a film of gas 0.5 mm thick when the concentration change across the film is 10 to 5% ammonia by volume. The diffusion coefficients of ammonia in nitrogen and hydrogen are 1.89 into 10 to the power minus 5 meters square per second and 6.32 into 10 to the power minus 5 meters square per second respectively. So I have taken this numerical. This is a unsolved numerical from treble. I have taken numerical from treble, and we are supposed to solve this. So ammonia is diffusing through a stagnant mixture consisting of 1/3 nitrogen and 2/3 hydrogen by volume. So this is the statement, and after after reading the statement carefully, we have to identify the case. What type of diffusion is this? Which case is involved in that particular diffusion process? We first have to identify that. So that's why I have set the task of identifying the case. Let us first identify. By reading the statement carefully, we are going to identify the case. So if you read the statement carefully, you will come to know that this is diffusion in a 3-component gas mixture. So this is a case of multi-component gas mixture. There are 3 components. Which are these 3 components? You have ammonia, then you have nitrogen, and you have hydrogen. The third component in the mixture is hydrogen. So clearly it is a case of diffusion in a 3-component gas mixture, that is multi-component gas mixture. The other thing that we have to note over here is, if you read it, what they say, they are saying ammonia is diffusing through a stagnant mixture. So ammonia is the diffusing component, and it is diffusing through a stagnant mixture. The mixture of remaining 2 components is stagnant. The mixture of remaining 2 components is not diffusing. So that we have identified over here. Only one component is diffusing. The other 2 components are stagnant. So now the case is clear to us. This is a case of molecular diffusion in a multi-component gas mixture. To be exact, there are 3 components. The components are ammonia, nitrogen, and hydrogen. Only one component, that is component ammonia, is diffusing, whereas the remaining 2 components, nitrogen and hydrogen, they are stagnant and they are not diffusing. So the case is now identified. Now after that, let us solve. Once we know what is the case, because identification of the case will help us to know which equations are to be used for solving the numerical. Multi-component gas mixture, only one component diffusing, all other components are stagnant. Okay, so let us move ahead. So let us go for the solution for this numerical solution to the numerical. So to begin with, we are going to use notations. What are the notations? We are saying that A, let A represents ammonia. Component A is nothing but ammonia, and that is the diffusing component. Then B is the second component in the mixture, that is nitrogen, and C is hydrogen, the third component in the mixture. Okay, so we are starting with by define or by stating these notations. A is the diffusing component, that is ammonia, B is nitrogen, and C is hydrogen. Okay, now let us whatever is given in the statement, let us try to represent it schematically. So that's why I am saying let us have the schematic drawing for the diffusion process, schematic of the drawing. Okay, so you have two planes and distance between those two planes is 0.5 mm. This is given in the statement. If you go back and refer that statement, you will come to know that the distance between the two planes is 0.5 mm. Okay, that this is one thing. Then on one side of the at one plane, composition of ammonia in the mixture is given. So at one plane, the composition of ammonia is there is 10% of ammonia by volume. Composition is given by volume. Whereas at from this plane, ammonia is diffusing to the other plane. The direction of diffusion or how concentration will change along the diffusion path I have shown over here, and it is diffusing to a plane where concentration is 5% of A by volume. So diffusion is taking place from 10% volume, 10% of ammonia by volume to 5% of ammonia by volume. So diffusion will always occur from a place of high concentration to a place of low concentration. Okay, so this is the schematic representation for the system. What other information is available with us? The other two components, mixture of remaining two components, that is nitrogen and hydrogen, B plus C. That mixture is stagnant. Only A is diffusing, and it is diffusing from a high concentration plane to a low concentration plane. The high concentration plane and low concentration plane, they are separated by a distance of 0.5 mm. This is what is given in the numerical statement. Okay? Then after that, temperature is given to us. Temperature is 54 degrees Celsius and we need it in Kelvin. That's why I have converted it to Kelvin. So 54 degrees Celsius is 54 plus 273.15, that is 327.15 Kelvin. So temperature that is given in degrees Celsius to us, we have converted it to Kelvin. The other information is pressure is given. It is 206.8 kilonewton per meter square, and if we convert it to Newton per meter square, we will have to multiply with 10 to the power 3. So it is 206.8 into 10 to the power 3 Newton per meter square. Again, then diffusivity is given. You have two diffusion coefficient. One is diffusivity of A in B, diffusivity or diffusion coefficient, one and the same thing. So DAB, diffusion coefficient of A in B, diffusion coefficient of ammonia in nitrogen, it is given as 1.89 into 10 to the power minus 5 meter square per second. Please note this value of diffusion coefficient is at this temperature and pressure. So at the given temperature and pressure, diffusion coefficient of ammonia in nitrogen, that is DAB, that is 1.89 into 10 to the power minus 5 meter square per second. This is given to us. Then the other diffusion coefficient, it is also given. Diffusion coefficient of A in C, diffusion coefficient of ammonia in hydrogen, it is given as 6.32 into 10 to the power minus 5 meter square per second. Okay, then distance between the planes is given. I have shown over here. It is 0.5 mm, but we will convert it to SI system. So Z is 0.5 mm, that is 0.5 into 10 to the power minus 3 meter. Okay, then second thing, this is the schematic representation. Second step that we have to uh, second step in the calculation is we have to find mole fractions, that too on a free basis. Okay, so how to get this, let us understand. Now in the stagnant mixture, of B and C, what is the composition of the stagnant mixture? In that stagnant mixture, there is 1/3 of B and 2/3 of C by volume. So 1/3 part of the mixture is B by volume, 1/3 volume of the mixture is B, and 2/3 volume of the mixture is C. Okay. Now, how to convert this information into something that is understandable? Understandable. Let us understand this. So, from this information, we can directly know what is the percentage volume of B in the mixture. So percentage volume of B in the mixture is 1 by 3 into 100, 1/3. That is, out of total 3 volume units, 1 volume unit is of B. So volume percent for B will be 1 by 3 into 100, and that comes out to be 33.33%. So now we know percentage volume of B in the stagnant mixture is 33.33. Okay, similarly, percentage volume of C in the stagnant mixture is 2 by 3 into 100, that is 66.67. Out of the total 3 volume units, 2 volume units are of C. Therefore, volume percent of C is 2 by 3 into 100, which comes out to be 66.67%. Okay, then we are going to assume that the system or the mixture is behaving ideal gas behavior. If you assume that, what is the benefit of that? If you assume ideal gas behavior, we can set percent volume is equal to percent mole. So whatever percent volume you have for B and C, that is nothing but percent mole of B and C in the mixture, and percent mole can be converted to mole fraction by dividing with 100. And the mole fraction that we'll be getting will be nothing but mole fraction on a free basis, because you see nowhere we have considered a in the calculation. So mole fraction that we will be getting by doing all this exercise is the mole fraction on a free basis. So as per our notations that I have used in my previous discussion, link is given in the description section. So as per our notation, y dash b, that is mole fraction of b on a free basis, dash indicates this is being taken on a free basis. So y dash b is equal to 0.333. Simply 33.33 is divided with 100, and y dash c, that is mole fraction of c on a free basis, is 0.667. Simply 66.67 divided by 100. Okay, so on this slide we have basically written the given things. We have changed them into appropriate units, and from the information about the contents of the stagnant gas mixture, we have found out y dash b and y dash c, because we need this in our calculation. Okay, so on this slide we have written all the given things, and now we know what is y dash b and y dash c. Okay, now let us move ahead. So let us continue with our solution. So next step, after knowing y dash b and y dash c, as we did it on the previous slide, now we can directly calculate effective diffusion coefficient, and for that the formula is known to us. Formula for calculating effective diffusion coefficient is DAM is equal to 1 upon Y dash B upon DAB plus Y dash C upon DAC. DAB and DAC, they are already given to us, and in the previous step we have calculated Y dash B and Y dash C. Okay, so we just have to use the values that are given to us. So we just calculated Y dash B to be 0.33 and Y dash C to be 0.67. So it is 0.6667. So we can truncate it to 2 digits. So it is 0.67 and this is 0.33. DAB is directly given to us in the statement. It is 1.89 into 10 to the power minus 5 meters square per second. DAC is given to us. It is 6.32 into 10 to the power minus 5 meters square per second. Now you just have to use this in the formula. So placing everything at their appropriate place, you get this. Okay, so DAM is 1 upon 0.33 divided by 1.89 into 10 to the power minus 5 plus 0.67 divided by 6.32 into 10 to the power minus 5. And if you solve this, you will come to know DAM comes out to be 3.56 into 10 to the power minus 5 meters square per second. Okay, so at the end of this calculation, we know what is the effective diffusion coefficient of component A in the mixture, and that is the only component that is diffusing. Okay, so that ends calculations for this for the effective diffusion coefficient. So at the end we have got a value for the diffusion coefficient. Okay, then after that the last step is we have to find out the rate of diffusion, because they have asked the rate of diffusion. So let us calculate that. So clearly, while identifying the case, we have found out that this is a case of A diffusing in a non-diffusing gas mixture of B plus C. And for this case, I have already discussed this in my previous video. What is the point? A and B plus C have their partial pressure. So A will be exerting its partial pressure, and B plus C, the stagnant mixture, will be exerting a combined partial pressure. Okay, the case I have already discussed. The rate of diffusion for this case is given by this formula. Again, how the formula is applicable over here, I have discussed in my previous video. So it is Na is equal to DIM into P divided by RTZ PBCM PA1 minus PA2. Okay. Now, right now, PA1, PA2, these are not known to us. PBCM is also not known to us. So first we will have to get values for this 3, and then we can solve the equation. We can use the equation to get the value of Na. Ultimately, we will have to get value for, we are supposed to get value for Na, that is the rate of diffusion. Okay, so let us move ahead. So on the side, we have understood which equation is to be used. Okay, so again, we have already done this. We have assumed ideal gas behavior. So again, the diffusion schematic of the diffusion process, I am taking this on this slide for our reference. So YA1 is 0.1. Now why it is 0.1, you must have understood it, or I will explain it. So on high concentration plane side, concentration of A is 10% by volume. If you are assuming ideal gas behavior, percentage volume is equal to percentage mole, and percentage mole will be converted into mole fraction by dividing with 100. So 10 by 100 is 0.1. So YA1, that is mole fraction of A on high concentration plane. Let this plane be identified by 1 and this plane be identified by 2. So at this plane, at the high concentration plane, mole fraction is 0.1. So accordingly, we have YA1 is equal to 0.1. With similar explanation on the low concentration plane side, concentration is 5% by volume. This is 5% by mole, as we have assumed ideal gas behavior. And when you divide it with 100, that will give us mole fraction. So mole fraction of A on the other side is Ya2, and that is given to us. It is 5 divided by 100, that is 0.05. Okay. So this is how we get mole fractions. Further, if we know the mole fractions, you can calculate partial pressures. So with Ya1, we will be calculating Pa1, and with Ya2, we will be calculating Pa2. Again, for that, what we know? We know partial pressure of a component in a gas mixture is equal to mole fraction of that component in the gas mixture into total pressure. Okay. So if mole fraction and total pressure is known to us, you can get partial pressure. So partial pressure is mole fraction into total pressure. Similarly, for at the other end, Pa2 will be mole fraction at that end into total pressure. Total pressure is given to us. It is 206.8 into 10 to the power 3 Newton per meter square. So Pa1 will be equal to Ya1 is 0.1. Total pressure is 206.8 into 10 to the power 3. So it is 0.1 into 206.8 into 10 to the power 3. That comes out to be 20680 Newton per meter square. 20,680 Newton per meter square. Then second is in the same way you have to get Pa2. So Pa2 is Ya2 into P. Ya2 is 0.05. So 0.05 into 206.8 into 10 to the power 3, that comes out to be 10,340 Newton per meter square. Okay. Why we are taking pressure in Newton per meter square, that is Pascals? You'll come to know. I'll discuss that in my further discussion. Okay. So the point is, by assuming ideal gas behavior and using these relations, we have found out Pa1 and Pa2, because we need this in the equation that we are supposed to use. Okay. Then the next step is calculation of PBCM. And if you have referred my earlier video, PBCM is PBC2 minus PBC1 divided by ln of PBC2 by PBC1. How to get PBC2? PBC2 is total pressure minus partial pressure of A at the second plane. Similarly, PBC1 is P minus Pa1, total pressure minus partial pressure of A at the first plane. So PBC2, by using this formula, you'll get PBC2, total pressure minus Pa1. So it comes out to be 196,460 Newton per meter square. 1,96,460 Newton per meter square. Then using the second equation, PBC1, equation for PBC1, you get PBC1. So it is 206.8 into 10 to the power 3 minus 20,680. So that comes out to be 1,86,120 Newton per meter square. Okay, is that clear to you? I hope this is clear to you. If you have any doubts in any of the state, you please mention that in the comment section. Okay, now once PBC2 and PBC1 both are known to us, you can straightforward do the calculations for PBCM. So you put all the given all the calculated values, PBC2, PBC1, and then finally you'll get PBCM. So PBCM comes out to be 1,91,243.41 Newton per meter square. So this is the logarithmic average of partial pressures exerted by the stagnant mixture. We need PBCM in the calculation, so that's why we have calculated over here. Okay. So on this slide, we have now we know what is Pa1, what is Pa2, and what is PBCM. Okay, now let us move ahead. The equation to be used is known. We have already understood this. So this equation has to be used. All quantities are now known. All quantities required on the right hand side of the equation, they are now known. You just have to put those values and get Na. Okay, so DAM we calculated it previously. It is 3.56 into 10 to the power minus 5 meters square per second. Total pressure is 206.8 into 10 to the power 3 Newton per meter square. Then next is PA1. PA1 we calculated it is 20,680 Newton per meter square. PA2 it is 10,340 Newton per meter square. Then R, the value of R we know it is 8.314 joule per mole per Kelvin. Now let me talk about it. Let me talk about it. Talk about the value of R. Okay, so it is R. I have given it as or over here the value of R is 8.314 joule per mole per Kelvin. Okay, now joule is nothing but Newton meter. So that is equal to 8.314 Newton meter per mole per Kelvin. Okay. Now I will bring units for pressure over here. What is the unit for pressure? It is Newton per meter square. So in order to have Newton per meter square on in the numerator, what I have to do? I have to divide with meter square and multiply it with meter square. So it will be Newton per meter square into meter cube. So the value comes out to be 8.314 Newton per meter square into meter cube per mole per Kelvin. Okay. So now 8.314 joule per mole per Kelvin is nothing but 8.314 Newton per meter square into meter cube per mole per Kelvin. So you have unit for pressure, you have unit for volume, you have unit for amount of substance, and you have unit for temperature. So R is 8.314 Newton per meter square into meter cube per mole per Kelvin. Okay. Now my point is, if I use this value of R 8.314, I'll have to keep pressure in Newton per meter square. Volume will be in meter cube and amount of substance will be in mole. Now if I want it in kilomole, one mole is 10 to the power minus 3 kilomole. So I'll show that. So that is R is equal to 8.314 Newton per meter square meter cube divided by 10 to the power minus 3. Now it is per kilomole per kilomole per Kelvin. Okay. So what I have done in the final step, I have converted this moles to kilomole, and for that I have this figure 10 to the power minus 3 in the numerator, in the denominator, sorry. So that means R is 8.314 divided by 10 to the power minus 3 is nothing but into 10 to the power 3. So 8.314 into 10 to the power 3 Newton per meter square meter into meter cube per kilomole per Kelvin. So the point is R, if I use this value of R, 8.314 into 10 to the power minus 3 is 8314. If I use this value of R, what will be its units? What will be its unit? It will be Newton per meter square into meter cube per kilomole per Kelvin. Okay. So if I use value of R as 8314, I will have to keep pressure in Newton per meter square. So that's why everywhere I have used pressure in Newton per meter square. Volume, has to be in meter cube, but there is no volume in the equation, so that is not a problem. But the amount of substance that you'll be getting, it will be in kilomole. That is, the rate that I'll be getting will be in kilomole per meter square per second if I use this value of R. Okay, so you please remember, be careful while using the value of R. Okay, so I'll be using this value of R, and due to this I'll have to keep pressure in Newton per meter square, and rate that I'll be getting will be in kilomole per meter square per second. You please understand this. If you have any doubt in what I have just shown, you please mention that in the comment section. Okay, so I'll just rub it. I hope you have understood my discussion. You can just rewind the video and just understand what I have just discussed. If you still have any doubt regarding that, you please mention in the comment section. I'll explain that. Okay, so R is 8.314 joule per mole per Kelvin, but I'll be using it as 8314 kilonewton per meter square into meter cube per kilomole per Kelvin. Temperature we have noted down previously, it is 327.15 Kelvin. Z is 0.5 into 10 to the power minus 3. PBCM we calculated on the previous slide, it is 191243.41 Newton per meter square. So all values are known, you just have to put all the values in this equation and get the final answer. So if you put all the values, use your calculator properly, carefully, you will get the final answer, and the final answer comes out to be 2.93 into 10 to the power minus 4 kilomole per meter square. Why I have got it in kilomole? Now I hope it is clear to you, because we have used equation value of R accordingly. So you just check value of R that I have used, it is 8314, and that's why the answer that I'm getting is in kilomole per meter square per second. Okay, so in this way we get the final answer, the answer that we needed in the solution. So rate of diffusion is 2.93 into 10 to the power minus 4 kilomole per meter square per second. Okay, so with this I end my discussion for today's video. I hope you have understood the numerical. If you have any doubts, you please mention in the comment section. Please subscribe to my channel for more such videos, and then tell your friends to subscribe to it. Hit the bell icon so that you will immediately get notified as soon as I upload any video. For time being, thank you for being with me, and continue to be with me in future also. Thank you. Bye bye. Have a great day.